Hello, welcome back to my lectures on industrial organizational psychology. This is the second lecture. Last time I talked about the bit of the history of industrial organizational psychology, some of the major movements that have occurred in it. Today I'm going to give a basic background of science, statistics, and basic research methods. I have a playlist that is slowly growing on my research methods course for business students. It's called Mana 420. But here I'm going to focus on real basics. This is more of a refresher course. Some of the statistics things should be familiar if you've ever taken a statistics course. And in general, in this class, we need to be able to understand what the concept is rather than necessarily be able to apply it in a technical setting. I mean, that would be ideal. And I will at some point probably be putting up similar lectures to this one on statistics as well. A little bit of a trifecta there. So the learning objectives today are to understand something like the real scientific method. I'll present it as it usually is presented in textbooks, but try to talk about it in a way that's a little bit more concrete. So we introduce some of the basic vocabulary used in psychological science, particularly some somewhat odd words that people may not, even people familiar with other sciences may not be familiar with, particularly things like construct and operationalization. Again, a refresher on the usual statistics we use, including mean, standard deviation, correlation, multiple correlation, mean difference, and what do they tell us? And just talk a little bit about what we mean, well, what I mean when I say something about data worlds versus theory worlds. So here's what our basic standard sort of scientific method looks like in the textbook version. So you start off with some kind of an observation about about the world. Yeah, sorry, I'm not sure why that happened. And based on that observation that you have, whether this is some sort of a problem facing maybe an organization you work in, you develop a hypothesis. And again, this is usually within the framework of a larger theoretical model. But in general, so for instance, classics that will come up in throughout this course are some often simple bivariate hypotheses. So something along the lines of when workers are more satisfied, they have better performance or more productive. These sorts of things might be the hypothesis might be all else being equal, smarter people perform better. People who experience greater degrees of fairness in their organization are more satisfied by their jobs. So things like that. We then gather data. Let me just try this one instead. Maybe that'll work a little better. There we go. Well, it's going to be an ugly color setting. Okay, so we gather data, and a lot of times, again, in industrial organizational psychology, often this is either survey data or sometimes some sort of field quasi-experiment. It's rare outside of maybe more direct tests of theory, usually with student populations, but sometimes with online or panel, like research panel samples. We sometimes have true experiments, but in general, most of this is observational, correlational, or non-experimental research. We'll then test the hypothesis using usually some of the statistics I talked about before, and if that test is successful, we will accept the hypothesis. I want to be clear that when I say accept, I don't mean that we necessarily believe that the hypothesis is true, or certainly at least not the whole truth. And it's more taken as a piece of what economists sometimes call a stylized fact. That again, so like for instance, in general, the evidence does point to something like measured cognitive ability does substantially, or at least most substantially, predicts individual job performance. Certainly as assessed by supervisor assessments, but also by most objective measures and things along those lines. Lots of evidence for that. Now, I'm not saying, but again, there are questions about what does measured cognitive ability actually assess. People often call it synonymous with intelligence, but I don't want to overemphasize that. Similarly, the other examples that I mentioned is something about when workers are more satisfied by their jobs, they also perform better on their jobs. There's fairly weak evidence for that. A lot of the correlations are pretty small there. And again, that doesn't necessarily mean that there is no interest, like an organization should have no interest in an employee's job satisfaction. Because employees who are dissatisfied are far more likely to turn over, which is, again, that leads us into this zone where we must revise our hypothesis. So again, not much evidence for that, what's sometimes called a happy productive worker hypothesis, satisfaction being possibly associated with performance. So we might have to go back and revise that. Maybe there is some reason that satisfaction doesn't predict performance very much, which would then lead us to cycle through this again as many times as it might take until we think that we have some kind of an understanding about why this original observation occurred. And again, we need new data every time to test that hypothesis, to test the new hypotheses. We can't just go back to the same well. That would be problematic for statistical reasons. Here we go. Our key statistical concepts here. I just realized I hope the laundry machine isn't the microphone isn't picking this up too much. But anyways, our first key statistical concept is that our variables are in fact that they're variable typically over people, but it's also over time. So they're often sampled. So any observation of that variable is sampled from a distribution. Oftentimes, our typical assumption is that that distribution will be a normal or Gaussian distribution. The familiar and nearly infamous bell curve. So, for instance, here this is a representation of a variable being sampled. So this symbol here, sometimes called the twiddle, it can be interpreted as is distributed as. So X is distributed as this italicized capital N refers to the normal distribution. This is its mean, 0, and its variance, sigma squared, which describes essentially how wide this is. But we'll talk more about that in a minute. Now, most of these distributions, certainly anything in sort of like this, well, certainly a normal distribution, are characterized by their center, which we often assess by the mean, but there are alternatives, and we'll mention that in a moment. And their spread. So the standard deviation, I'll see if I can do that decently, is going to cover one standard deviation below and above the mean are going to cover 68% of observations. 2 standard deviations are going to cover 95% of the population, and 3 standard deviations are going to cover 99%. So as we get out into these zones, which are usually referred to as the tails of the distribution, we're describing fewer and fewer people. So again, like for the refresher here, the height of this distribution is the frequency with which observations of these values we should expect to occur. So with a normal distribution, the mean is going to tell us essentially what is the most likely observation. So with a normal distribution, this is equivalent to the mode. It's also equivalent to the median or the middle observation in a true normal distribution. That's not always going to be the case for other distributions, like things that take all positive values, like say income or wealth, are not normally distributed, and the mean does not characterize that very well. Like the the extreme spread of values out to the high end will bias the mean upwards, whereas the median will stay relatively unaffected by it. It will just like therefore like Bill Gates contributes the same to where the median is as a person making minimum wage. So for some variables that have a heavy tail, other measures of the center can be better. Other distributions, we sometimes use these guys in particular. We're not going to talk about this a lot in this course. If you do see my the statistics course that I mentioned, if I get that posted anytime soon, you'll see a little bit more of this. So in particular, we often use for data that has some sort of account structure. So for instance, like maybe number of goals in a soccer game or number of widgets someone produced, possibly even um, other things, football goals, perhaps. Well, I already said that more or less with soccer. But anyway, something along those lines. We'll use something in the Poisson family to describe that. Depending on the structure of the data, we might instead use a negative binomial. Or a zero inflated Poisson if we expected a lot more zeros. So this might be good for something like goals in a typically low scoring game like hockey or soccer. And similarly, depending on the structure of the data, we might prefer, similarly zero inflated but negative binomial. The binomial is also pretty common throughout statistics, being able to model zeros and ones, heads and tails, pluses and minuses, binary agree versus disagree responses, things like that. Membership in a binary category. Um, this comes up a fair bit, although not a lot in industrial organizational psychology applications, but it's used quite a bit. Well, I should say maybe a fair bit. And there's yet others, but they're even rarer. For instance, sometimes people like to discuss power law distributions, which first occurred in the study of wealth in the late 19th century by the economist Vilfredo Pareto. And it hardly ever fits real data, despite some interest in this concept over the last 5 or 6 years, looking at individual job performance. But in general, our key statistical concepts are measures of central tendency. I mentioned most of these before. So the mean, or the actual arithmetic average that most people are familiar with, the median, like I said, the middle value, and the mode. As I mentioned before, in a normal distribution, which many variables we deal with are at least approximately normal, these are the same or in empirical data very close to one another. And this is good for answering questions about what is a typical or representative value of the variable. So if we're trying to make a comfortable new car seat, what's the typical height of drivers in the US? So something that accommodates the average comfortably is a good choice. There. Measures of dispersion, on the other hand, are useful. So I mentioned the standard deviation. That's pretty common. If you squared it, you have the variance. So they communicate some similar information. Sometimes the range is particularly useful. So what is the tallest driver in the United States versus the shortest driver in the United States for the car seat example up above? But in general, that can go along with the the question here that we're really looking at is how much do values typically differ from one another? So again, so we want to have some idea of how wild, like if we take two observations, something with a narrow standard deviation, narrow range, or just in general narrow dispersion, two random observations from it are not likely and again, I mean likely. This is not guaranteed to be true, but they're not likely to be different, too vastly different from one another. Whereas something with a large dispersion, any two randomly sampled observations of it could differ quite wildly. Again, could. They could wind up being quite close. And I mean, that's the nature of probability. Again, if you deal a hand of cards, it's possible that you could have all four aces in it. That doesn't happen often, but it does happen. So, not everyone, the idea here is certainly not everyone is average height, and in truth, no one is exactly average height. But well, that's exactly it. So how much do people differ? How much on average do drivers deviate from the average? This could inform, again, from this perspective of what is, if we're trying to make a comfortable new car seat, we want it to be like the middle of its range of adjustment. We probably want to be at or approximately close to the mean height, but we want typical variation in height to be accommodated by the range with which you can adjust it. So we want the shortest typical driver to be comfortable driving with the car seat at its smallest adjustment, and the tallest typical driver to be comfortable with its largest adjustment. Now, of course, there might be people who drive who are short enough that they are not comfortable with the our shortest, and there may be people tall enough that they're not comfortable with our largest adjustability. So those we may not be able to accommodate everyone simply by taking into account typical dispersion. Correlation. We'll talk more about this, so I won't go into a huge amount of detail here, just describe what kind of a question we're going to ask or address with this, which is how much do two variables relate to one another. So apparently we find that taller drivers are less satisfied with our spiffy new car seats, right? So the taller a person is, the lower their satisfaction score is expected to be on this. Now, that's not to say that some short people aren't dissatisfied. That's not to say some average height people aren't dissatisfied. And that's not to say that there might be some very tall people who are completely satisfied by it. Again, this is all about typicality. The stronger the correlation will be, the less the sort of atypical observation should be expected to occur. And just for what it's worth here, we'll talk about this in more detail in a moment, but what I'm describing here is a negative correlation. As one variable goes up, the other variable goes down. And multiple regression or correlation analysis is very similar, except this can be used for prediction. So we want to know specifically how much do two or more variables relate to some other variable. Again, we can do this with one variable in a simple regression framework, but what we really want to be able to do is say maybe predict the level of satisfaction that a driver of a particular height would have. So we want a regression equation. We can just take the person's height and any other, maybe some other variables that we're interested in, plug those into the regression model, and predict their expected level of satisfaction. This is, again, useful in business applications for maybe possibly for forecasting demand based on certain market factors that are measurable ahead of demand. It might be useful for, it's useful for, this is variations, often sophisticated variations on this technique are used to predict the outcomes of elections, things along those lines, or the outcome of a sporting event ahead of time. So that's it. So we see that people who are taller and heavier are dissatisfied with our seats. Are both height and weight important for satisfaction? So those are the kinds of questions that we can ask with this, and also it can produce additional tools that we can use. Mean differences, which are typically in this field, are going to be assessed using t-tests or ANOVAs, but there was other techniques like permutation tests and so forth that can be done here. In general, let's say we are testing out, we have two new designs and we want to see on average, do people on average prefer design A or design B? That's the kind of question we can ask here. And ANOVA, it just extends this out and say we had 3 new designs or more, then we would be asking the same question, which we can ask, which one of, do people differ in how satisfied are they by it? And we can add some additional calculations to this to determine which is the most satisfying. So here is examples of various kinds of correlation. So on this side, this is, a very strong, in fact, as you can see, this is pretty much hugging the 45-degree line. So this is a nearly perfect correlation. And again, reminder, the correlation ranges from -1 to 1 inclusive. Right? So this is going to be very close to a +1 correlation. There's a little, as you can see, there's a tiny bit of wobble there, so it's probably not exactly perfect. And the same thing here. This is a representation of a negative correlation, because as you can see, as the x-axis values increase, the y value axis decreases. This is a representation of a very, 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 very weak correlation, probably close to 0. Here we're seeing that, as as the x values increase, the y values are scattered all around it. Like a 0 correlation, like these dots would be probably pretty well described by, a circle, or depending on how the range, maybe just a flat bar around, flat box around this. And we'll see this. I'll often later on in the semester use just circles and ovals to represent these dots, which are formally, if you're unfamiliar, this is a scatter plot. Over here, this is a positive correlation. As you can see, it's shaped similar to this, but again, there's more spread around the axis here. So this is a weaker correlation. It's still very, probably a much stronger correlation than we're likely to see in data in this field, but it's weaker than this one. This one here is weaker than this one, where again, this is probably very, very close to 1. This one's very, very close to -1. This one's going to be a bit weaker, but still probably pretty, looking at this is still going to be pretty strong. This is going to be probably around correlation of 0.8 or something. I just want to take a moment to talk about effect sizes, because in this course, I'll probably mention a bit about statistical significance, but we're usually more concerned with the size of an effect. So the mean difference between men and women on something, or the mean difference between, again, the 2 different car seat designs. Maybe people prefer design A to design B, but we want to be able to say, does it matter? And that can't be asked by statistical significance. That's a question that cannot be answered by statistical significance. We need to know something about practical significance, and so effect sizes are often useful for this. So mean differences, so the t statistic in a t-test can usually be transformed in fact, as a rule, can be transformed into an effect size. So with a mean difference, this is usually standardized into some form of a deviation metric. So we would be able to talk about, on one of the two, if these 2 groups were measured on exactly the same scale, we could be able to talk about how many standard deviations the means are apart. So maybe it would be 0.8 of a standard deviation is generally considered a large and very robust effect in this setting. Because again, just to be clear, that means that it's 80% of one standard deviation. So that's a fairly substantial bit above the mean. Furthermore, a correlation is typically considered directly an effect size, although some people will prefer the squared correlation, which I'll describe in a moment. But one thing to remember about a correlation is that it only captures a linear relationship. So for instance, this scatter plot, which is just generated very, very quickly in Excel once upon a time, there is actually a pretty robust relationship here. To the extent of my ability to draw, this is a quadratic or parabolic relationship. So as x increases, y first goes up to an inflection point and then comes down again. And again, it's fairly strong. As you can see, these the observation, the points representing the observed values for these variables, well, they don't spread too widely around that parabola that describes the functional form. A correlation, like the correlation for this is going to be maybe because there's a few more observations on this side where it's sloping down, that this might be slightly negative, but it's going to be very, very close to zero, which is going to say, like, if people don't look, if no one, if, you know, a scientist, a researcher, doesn't look at the data here and they only calculate the correlations, this is going to look like a zero correlation. It's going to look like a flat line. It's going to look like there's nothing going on between these two variables, where in fact they actually have a pretty robust relationship, just that relationship is not linear. It's curvilinear. Now, of course, this can be captured quite easily with a number of statistical techniques, some more advanced that we won't really talk about in this class, like various smoothing techniques, like low S smoothers or smoothing splines, or simply in this case where the actual relationship has a very nice and pretty easily inferred functional form. This can be captured using regression, polynomial regression, quite easily. Correlations, as I mentioned on the last slide, are generally considered effect sizes or measures of effect. And so as I was trying to illustrate that these are ways of describing how big or important a variable is, especially in terms of discussing how important it is to some sort of like important dependent variable or outcome that we might want to do our best to optimize that outcome. Understanding which variables will most strongly contribute to the value of that variable can be very, very helpful. So again, these tell us, effect sizes tell us this. And again, as I mentioned, it's related to, but very distinct from statistical significance, in that, you know, in general, like all else being equal, like so the same sample size, the same research design, all of that. If you have a larger effect size, you are typically going to have a more significant effect. So as the effect size goes up, the p-value goes down, all else being equal. We won't talk a lot about statistical power in this class. Again, I do intend to post lectures about statistics at a later time. So if any of those things intrigue you and you're not familiar with them, or you remember them from a previous statistics class, want a refresher, hopefully I can help you out at some point in the not too distant future. But just describing this in terms of like, and again, these are just rules of thumb. Like if we want to try to figure out on a correlation scale, what is important, what's a substantial relationship. In general, you know, these are, as I say, just rules of thumb. This is not something that there's extremely good reason for, but in general, we definitely consider effect size. Well, under most circumstances, we consider effect sizes of less than 0.1 small. Maybe not trivial. That would be like a term that we'd use for correlations very, very close to zero under most circumstances. In this field, you know, a correlation from like 0.2 to 0.3 is modest or medium. This is actually where a lot of the correlations that we'll see like for individual variables predicting individual other variables, this is not uncommon. Like this is generally, like for instance, a fairly, you know, been fairly robustly demonstrated that the Big Five personality characteristic conscientiousness predicts individual job performance pretty decently, and it's going to be in this range as well. I mean, that's a pretty well replicated effect, but it is not huge. And things greater than 0.3, a lot of times people will actually say 0.5. That's when people are going to consider this large. So for instance, as I mentioned before, and we'll see later on in the semester, the relationship between measured cognitive ability and especially like say supervisory performance evaluations is around here. And for what it's worth, like, and if you square this correlation, people interpret that as the percent of one variable explained by the other variable, and so if we square this, that's going to be around 25%. So even our probably best individual predictor of job performance measured cognitive ability explains about 25% of the variability in individual job performance. So being the single best predictor, still not that strong. But again, like I said, it's our single best predictor. So, this is a number that we're going to probably wind up respecting quite a bit. And just to be clear, something I like to point out is just because a correlation is small doesn't mean that it's non-trivial, or that it is trivial. Sorry. So, for instance, like on a correlation metric, the effect of, taking daily 80 milligrams of aspirin and not having a heart attack is probably around 0.04. So really small, right? But that translates into basically a 40 no, yeah, 40 persons per 100 not dying versus dying. So if we have people not taking that daily 80 milligrams of aspirin, about 60 of them will have a heart attack and 40 of them will not, versus any of this for particular risk groups, right? Just an illustration, versus on the aspirin, that rate flips, and you can demonstrate this with something called a binomial effect size display. But so 40 people will not have a heart attack. 40 people will have a heart attack and 60 people will not. So just adding that daily 80 milligrams of aspirin, again, that's a 40-person swing for not having heart attacks. So again, really small correlation, but a fairly profound effect. So again, I want to be clear that effect size is not the only thing that matters in determining practical significance. We also have to think about sort of like the utility of using the variable that we're looking at as an intervention. And aspirin is a pretty easy intervention, and it has pretty decent outcomes for how easy and cheap it is to implement. And this is just to try to illustrate concepts of mean difference. So we want to know, like in general, if we measure a variable on any two groups, those groups are going to differ. But the question is, do they differ by just a tiny bit? Let's say like not very much, or do they differ by a lot? So again, here these two normal distributions. We have the mean for this one here, the mean for this one here, and the mean difference is this. So this is what's going to be summarized by the t statistic, or an effect size measures the d that I mentioned moments ago. So that's what we're interested in. So again, as you can see here, the idea is, the farther these two means are apart, then the larger this statistic is going to be, or this measure of effect. Just a note on experiments. True experimental research is less common in industrial organizational psychology and organizational behavior than in most other branches of psychology, but more common than, say, sociology or economics. Although behavioral economics is built on a number of experiments, so I want to be clear there. And the main difference here is experimental control. Random sampling and random assignment allow the experimenter to vary only the independent variable of interest, and since we don't typically have that, and we have very little, we have effectively no experimental control in most surveys. Now, it is possible to design a survey, like a study that uses surveys, but has, say, differences in instructions or provided stimuli or something along those lines. So you can have a survey measure that has an experimental manipulation baked into it. So just to be clear, I don't want to say that this is completely separate, but there's essentially, like in the typical survey, there is no experimental control, and in the kinds of field experiments that we'll talk about, there's certainly less experimental control. Oftentimes, a random assignment is not completely in the control of the experimenter. And even if it is, you generally don't have as strong control over the experimental environment as you would in a lab setting. So like random things that you might be able to control in the lab can happen much more often in field experiments, even if everything else about the design is pretty pristine. And just to take a moment here, a true experiment, we first are going to, and this is an idealization, we're first going to randomly sample from the population of interest, and this helps ensure what's sometimes called external validity. I prefer to talk about as generalizability. So, if we've got a nice, truly random sample from the population of interest, like we've got our population up here, we draw down our sample here, again, then the only thing, the only differences between the sample and the population are obviously its size, because the sample is much smaller than the population, but just sampling error, which is what the core mechanics of statistics is designed to deal with. So, this means that, anything that we can say about, anything that we can say about the sample within the limits of sampling error, we can say about the population. Then random assignment is going into a TET control versus an experimental condition. That's what gives us primarily our experimental control. So again, the idea here is you come into the lab, I flip a coin to determine whether or not you're going to be in the control group or the experimental group. So again, the idea here is like if we had a group, like the experimental group was all men and the control group was all women, any observations or if we observe any difference between those groups, it's hard to say whether it's due to the experimental manipulation or due to the sex differences. And that's true of any other characteristic. So if the control group and the experimental group differ too much on any characteristic, well, that could be an alternative explanation over whatever we did as an experimental intervention. And so we want to make sure that, again, up to the limits of probability, again, the randomness in the assignment, that that the control and the experimental group are the same. And again, such that the only difference between them is, the experimental group is exposed to whatever our manipulation is, and the control group is not. Now, of course, as I pointed out, when we deal a hand of cards, it's possible to get no ace, one ace, two ace, zero aces, one ace, two ace, three ace, or four ace. And all of those things can happen, but they happen with differing frequencies. So again, this is something that can happen with random assignment. Like we can do proper randomization and still get weird differences between the groups. But again, the larger our samples are, typically, the less frequently that kind of incidental alignment is going to happen. And the difference here being that in a field experiment, which a large number of the experiments that we might talk about in industrial organizational psychology are field experiments. Usually, I'll actually highlight that term there, field experiment. Usually one or more of these controls is missing. And in general, in IO, industrial organizational psychology, we cannot assume truly random sampling, because a lot of times we wind up getting, a sample from a particular organization or set of organizations, something along those lines. And so generalizability can be a concern. And as we'll see, we try to address this with something called meta-analysis a lot of times, but more on that later. So, and this is the last thing I seriously want to talk about. This is what I steal the terms here from a great professor of statistics in the psychology department at the University of Illinois, where I did my PhD, Larry Hubert, although he used the terms theory world and theory land, theory world and data land, if I remember correctly. But the basic idea is up here above, we have this sort of impenetrable border. This is on, if you've taken philosophy, this is an almost Kantian border between our theory and our reality, and the reality that we can actually see, touch, taste, smell, or otherwise directly observe. So up here, this is where concepts that we'll actually talk about more next week live. So these are what psychologists will refer to as constructs. So I might talk about something like, say, gender, dating success, sense of humor, attractiveness, intelligence, and interesting topics. So the basic idea here is that, in terms of articulating a theoretical framework, what we're saying here is that a person's chance of being successful at dating depends on having a sense of humor, but this is different for men and women, perhaps, attractiveness, and this goes straight to dating success. So we are saying that on average, more attractive people will be more successful. Here, on average, funnier people will be more successful, but funny men will be more successful at dating than funny women. Um, Intelligence, so again, smarter people will be better at dating success, but only because they have interesting things to talk about. So if you're a very smart person and the only thing you talk about is, say, like slime molds, which are fascinating, that you're probably not going to be too successful at dating. But if you have interesting things to talk about, so that you can have conversation with people, then you will be. So intelligence does not directly impact dating success, it indirectly impacts it. So if you've invested your intelligence in knowing interesting things to talk about with people, so you invest your intelligence in interesting topics, then you will be successful. But if you haven't, then you will not be successful. So this is what we will call a mediated relationship. So intelligence does not directly influence dating success, it is mediated by it. Similarly, up here, sense of humor does not have a direct impact, it is moderated by gender. So again, like in this case, we're saying that sense of humor is good for everybody, but it's better for men, just as an example. This is pulled out of the hat. Whereas attractiveness, this is a direct effect, right? Attractiveness, the better looking you are, the more successful you'll be. The other point to bring here is, now again, these are all just concepts. These are just things that live in my head, and now that I said them to you, they live, or at least are renting a room in your head. Now the question is, we need to pull those down into the real world. So we might ask, get a sample of university students and ask them about the number of dates that they've had this semester. Again, maybe this is a dated example since people, I don't know, people don't date anymore, right? But anyways, so that's our dependent variable, or as I'll often say in this class, outcome, or due to the history of industrial organizational psychology, this is often also called the criterion. Then we might simply ask people their gender, and obviously this could be a complicated question. A lot of times a survey might only give the traditional two examples here of male or female. But if we ask only that, maybe a lot of gender nonconforming people won't answer the question, or people misread it and read this, since we were talking about dating, maybe they read this as a question about their preference in dating, and so it may match their gender or not because they're actually asking a different question, or they may, as I said, or implied, may refuse to answer the question because the gender that they identify as is not represented on this. So again, this is a question here. Like up here, it seems conceptually simple because as we were talking about it, I was just talking about men and women. So maybe we might prefer to talk about biological sex, but even then, that might be complicated by a lot of the issues that I just raised. So this is the idea, is like something that seems conceptually straightforward. Is not the same. Similarly, we're calling this a dating success, and we're measuring it by the number of dates this semester. I've already pointed out that maybe this is an improper measure for dating success currently. And also, it's like we completely ignored the subjective issues. Like maybe somebody reports 2 dates this semester, but they had 0 the previous semester, so they consider that really successful. Whereas somebody else reports 2 dates, but they had 20 the previous semester, and therefore they consider it extremely unsuccessful. So even though this seems like a nice objective measure of dating success, hence this arrow pointing from here to the conceptual variable, but maybe it's not. Maybe it's not, and maybe we need a little bit something more subjective. Also, so with sense of humor, we say we're gonna, maybe have people come into the lab, tell a joke, and have a couple of trained raters rate that joke, their ability to tell that joke. Well, maybe we even standardize the joke so that everybody's telling the same joke, so we're actually getting at their ability to tell a joke, not their knowledge of jokes. But again, the raters, even if they're well trained, they may disagree in any or all instances. Again, training should have taken care of that. But again, this is just an example of, again, note this arrow connecting them, what we're trying to do with this observation, this measure, this assessment, trying to get at this conceptual variable. Same thing attractiveness. Maybe we measure the width of the nose. Maybe that's not great. Maybe like assessing the symmetry of their face would be better, or some combination of, say, symmetry, BMI, and with just go, I don't even know what all we could throw in there. Or maybe we should keep this more subjective. Maybe like we've done here, down here, having people raters rate this. Maybe we should instead bring them into the lab and have independent trained raters rate them on their attractiveness. Here, we've said intelligence, but as I've already pointed out, I'm saying we'll measure this using the Wonderlic personnel test, which is a test, a written test, written measure of cognitive ability, which, as I pointed out earlier, maybe that's not exactly the same thing as what people I shouldn't say naively, but what lay people mean when they say intelligence. And I think that there's some truth to that criticism. Maybe not as much as people think there is, but there is definitely truth to it. And then we might measure interesting topics with a current events quiz score. But again, that's fairly limited, right? We're just saying, like, do you know what's going on in the world? Most people probably do right now, and it may not be particularly interesting to talk about, since that's all people talk about currently. So again, the idea here that I'm trying to get at is we have to take up here in theory land these conceptual things that really just live in our heads, that we can't see or interact with in any way. We need to pull them down here into the messy world of data. We need some way of observing these things. And again, we'll talk about this is what I meant earlier. So these up here are what I referred to earlier as constructs. And down here, these are what I referred to earlier as operationalizations. So these are operational definitions of the things up here, or in the theory land side of this. Again, like I said, it's called the pseudo-Kantian boundary. But anyways, that's all more issues that we'll talk about next time when I introduce some concepts from psychological measurement and assessment, which I will include a little bit of critique of the way we usually do things. But anyways, thanks for your time. I hope this was moderately interesting, and certainly I hope it was helpful to some people out there. Thanks for, like I said, thank you for your time. As usual, if this was helpful or you liked it, please like. If you're interested, please subscribe, or at least keep checking back in. I'd appreciate it. All right, thank you so much. Have a good one. Bye.